Hello students, welcome back. Let us resume our discussion in section 3, the greatest common divisor. Previously, we went through the definitions of the GCD and the LCM, based upon the common idea that we had been going through since elementary school days. We proved both the GCD and LCD exist always and exist uniquely. What properties of the set of integers did he use? We used the fact that Z is discrete and totally ordered. Therefore, whenever it is bounded, we have a well-ordered set. Remember that? Bounded below, then well-ordered in forward direction. Bounded above, then we have well-ordered in backward direction. In the previous case, we have the minimum whenever you have a non-empty subset. That's how you get the LCM. And the latter case, whenever we hit a set that is bounded above, we have the maximum. That's how you get the GCD. Remember that? If you don't remember, you can always go back to the previous video and restudy those. Those are good, and those are, as a matter of fact, challenging enough, but still, we have to do more than that. You see? Proving what we had been doing for so many years since elementary school days and then getting the foundation done is important, yes. But equally as important is to go further from this point on. For that, we need some alternative tools. We're going to use two more alternative tools associated to the GCD and LCM. The first one shows up here, Bezout's theorem on the GCD. And that's associated to this expression here, down here, which is typically called a linear combination. So this kind of thing is called a linear combination of A and B. A times something plus B times some other thing. And in this case, everything is integers, so in the same expression, this D can be considered as a linear combination of X and Y as well. Also, a linear combination of A and B. But in general, things can get a little bit more messy, but that can wait. That's something we're going to do in linear algebra, not here. So that's a key point. And then there are a couple more aspects. What aspects? This one here, D divides A and D divides B, that is, D is a common divisor. And then finally this. D belongs to W. D is greater than or equal to 0. We have to focus upon these three properties. But the first one, green, is easy. This one is medium. And that one is a bit hard to apply, but it'll turn out to be the most important and useful. Let's finally begin Bezout's theorem. Enough preparation. Okay, given pair of integers A and B, there is a non-negative common divisor D. So non-negative so that means this green, and common divisor, that's blue. D divides A and D divides B. So the non-negative common divisor D of A and B of the form, now the red, the linear combination expression, or Bezout expression, named after French mathematician Bezout, D is AX plus BY. So with these three conditions, we can define appropriate integer D, because we can prove that it always exists, number one, and number two, it exists uniquely. Of course, we have to prove those to make this a well-defined quantity, right? But the proof is actually pretty difficult, very difficult, I have to say, and it is postponed until the end of this section. I can do it now, but if I do that, then after that, you're going to get exhausted and you won't be able to understand anything further. So it's going to be better to postpone it as much as possible. So for now, let's just assume that such an integer D with these three properties, green, blue, and red, exist. Let's take it for granted and we're going to prove it later. Now let's go to the next step. The existence we took for granted and postponed the proof. The uniqueness, we're going to prove it. Such an integer d exists, but not only that, it exists uniquely. What do you mean by that? If there were another integer, d prime, with all these properties, d prime is a whole number, d prime divides both a and b, and d prime is a linear combination, ax prime plus by prime, with some integers x prime and y prime, which may be different from those x and y, then this d prime and d will end up the same. That's what we want to prove. Along the way, we prove something very interesting on its own as well. Every common divisor divides this mysterious number d, which will later turn out to be the GCD. Any common divisor, C, that divides both A and B will divide D. And the proof of that is not too bad, but if you assume that, then we can prove that D and D prime divide each other. You see, D prime satisfies this one here, which I'm highlighting in blue. Yeah, a common divisor, that part, blue. So D prime divides D, and same thing goes here. D is a common divisor, so D divides D prime by the same code token. So they turn out to be the same because D prime and also D are both whole numbers. Let's prove the first line. And the proof is actually pretty simple. All you have to do is to utilize this. C divides A and C divides B. In other words, A is some integer times C, B is some integer times D. So from here, can you see that C divides AX plus BY? A is some integer times C, so AX is some integer times C. Same goes over here, so factor C out, C divides this entire thing, and this entire thing is D, isn't it? I'm highlighting this in red. Make sense? That's a whole proof, actually. Yeah, that is a whole proof. And if you really want to get to the bottom of it, then you can re-express C divides A into A is some C times some integer, like CS, and C divides B into B is some C times some integer, say CT, and then rewrite D AX plus BY as these and manipulate, factor C out. Yeah, you can get to the bottom of it if you want to. But I don't think that's really necessary if you already went through section 1 of this notebook. In section 1, divisibility, we went through all the properties of divisibility, all those. And linearity here, it's here, the linear combination thingy. Remember all those? Just different characters, that's it. So, any common divisor divides D. And then we can apply this very property with D and also with D prime. Because D is a common divisor, D divides a linear combination AX prime plus BY prime, which is this one down here. So D divides D prime. And also D prime is a common divisor here. That's the assumption, you see. And D prime satisfies all three, green, blue, and red as well. So D prime divides AX plus BY, this one here. Therefore, D prime divides D. And then please note that they are both non-negative. Therefore, D and D prime are the same. If one of them allows to become negative, in that case they may not be the same. Say for example, 2 divides negative 2. Negative 2 divides 2, you see. 2 times negative 1 is negative 2, and vice versa. So they may not be the same, but in this case they're both negative, so they are the same. So whenever you have a number that satisfies these 3 properties, number 1, whole number, green, number 2, common divisor, blue, and number 3, linear combination, red. Whenever you have a number that satisfies these 3, then that number is the greatest common divisor, D. So we went through this uniqueness, so we don't need this anymore. And let's get to this alternative definition. We can call such a number D the greatest common divisor of A and B, and we denote it as a GCD of A and B, or simply just A comma B when there's no danger of confusion. Now, is this definition of GCD and the previous definition of GCD compatible? Are they the same? That'll become clear in the proof of this part, which is 90% of this Bezout's theorem, as a matter of fact. But that's something I'll have to postpone. I can do it now, yeah, but it's gonna be a daunting task, and after that you're gonna get exhausted and you won't be able to understand anything at all. So let's just take this existence for granted, except that you have to remember these 3. Number 1, green, whole number. Number 2, blue, common divisor. And number 3, red, linear combination. That'll define the GCD uniquely. And among those properties associated to uniqueness, we have another additional property that is useful. Any common divisor of A and B divides D. So D is basically the least common multiple of all the common divisors of A and B, as a matter of fact, and that detail is left to the students. Okay, so much for the GCD and Bezout's theorem, at least for the time being. And let's consider just a little bit of applications of those, and then we're going to continue over the next videos. Okay, what's the first application? The integers A and B are said to be relatively prime or coprime if the greatest common divisor is 1. In this case, it comes down to the linear combination expression ax plus by is equal to 1. What am I talking about? The GCD has 3 conditions according to this Bezout's expression. Number 1, whole number, green. Number 2, common divisor, blue. And number 3, the linear combination, red. Remember this? RGB, green, blue, red, or whatever the order. But if your GCD is 1, then green and blue are automatic. 1 is certainly a whole number. Yeah, that's right. 1 is greater than or equal to 0, certainly. And 1 divides everything. So it's a common divisor of anything you can think of. So green and blue are automatic for 1. You only need to check red. So the relatively prime condition boils down to the red condition only. Ax plus by is equal to 1. Let's see. Shall we do an example problem that utilizes this relatively prime? Do you have time for that? Probably not. Let's stop here and let's resume in a separate video. We'll do a couple of exercises and then we're going to prove that Bezout's theorem later. Stay tuned. See you soon.